Okay, so good morning all of you. So I welcome you all to this first lecture on this second chapter, basically energy and its interaction. So am I audible to you, and is the screen visible to all of you? If yes, please say yes in the comment box. Am I audible to you? Okay, so see here. So if you see in the basic first chapter, Introduction to Thermodynamics, we have seen different basic terminologies that are involved, within thermodynamics. So, but in this particular chapter, we deal with energy interactions of the systems, of the systems from one system to one other system, or between systems and surroundings. Okay, so basically, we deal with the concept of heat and work. Concept of heat and work. Okay, so actually these two are the different other forms of energy that gets interacted. See, when you define an open system, we dealt open system as a system in which energy and mass interactions are permitted, correct? So we have stated another system which is called closed system, in which energy interactions only can take place but mass interactions are not permitted, correct? So in general, if you see what's the energy of a substance, of any system, of any quantity of matter that you contain, or a region of space. So if you see, energy is basically of two classifications broadly. One is macroscopic energy, and the other one is microscopic energy. Okay, so microscopic energy and macroscopic energy. Now, what is macroscopic energy? So if you consider the system as a single body, means as a single entity, then the energy possessed by this macroscopic motion of the system is called macroscopic energy. See, generally microscopic waiting. So something going wrong with audio or video? China, what's the problem? Waiting? Is everything going okay? Is everything going fine? Okay. Okay, so see here. So basically, this macroscopic energy, if you consider, macroscopic energy, if you talk about this, the energy possessed by the system, by the system as a single entity, means basically if you see the center of mass of the system or something, then based on the motion of that center of motion mass of the body, you define this macroscopic energy. For example, if you take a mass of block, then this mass of block which is having m, if this is moving at a velocity v, then we say the kinetic energy of this body is Ke is equal to half mv square, correct? This is what we state there. So similarly, if you see this block as a single entity, if this is at some elevation depending on some datum, then we say that this block is possessing some potential energy as well, correct? So basically these are macroscopic motions or macroscopic forms of energy that are involved when you treat the complete system as a single entity. But if you look at microscopic level, then what happens inside the system? There exists a lot of molecules, and these molecules also have motion. So that energy possessed by the molecules is called microscopic motion, okay, or microscopic forms of energy. So we'll see that. Microscopic energy. The energy possessed by the molecules of a system is called microscopic energy. Okay, so now what kinds of energy the molecules can internally have? Look, for example, let me draw some sketch for you, some good sketch. So you can see the things clearly. So now let us suppose there is a just a second, let me change the color for this. Okay, so see here, let us suppose you have a piston like this, okay, a cylinder like this, and in which you again have you know some piston like this. Okay, so then what happens, let us suppose these are the different molecules that are sitting inside. Okay, let us suppose all these are different molecules. Okay, so now if you look a bit deep into this microscopic energy of the molecules, then this microscopic energy is broadly classified into few types. So let us see what are they. Let's see, inside this molecules, inside this system, every molecule moves at some velocity, correct? Because of which we have pressure as well. See, if this is piston, for example, like this, then there is some exertion of pressure by this gas on this piston, because these molecules are not sitting idle, they are moving with some velocity, of course at a random motion, correct? So but since they have velocity and they are moving, they have one very important energy called translational energy, correct? So translational energy Now, why this translation energy is coming? Because these molecules which are here will start moving in different directions with some velocity, correct? There can be another molecule whose velocity is somewhere like this, and these velocity values may be different. They need not be uniform throughout this container, but in general this is called translation energy, because these molecules will have some velocity and they'll be moving. Now what happens, let us suppose these two molecules are connected by some bond, because molecules are generally connected by chemical bonds. So when they are moving, they can experience rotation, correct? So if you see, if this is a molecule, this is translation basically. So now if you see, if these two molecules are connected by a chemical bond, then what happens during its motion, this complete molecule can rotate, yes or no, because it's a random motion. So these two set of molecules which are here can rotate about some arbitrary axis. So we have a rotational energy, or basically a rotational kinetic energy, because when molecules are rotating, apart from rotating, they won't stay at a fixed point, they rotate and start moving. So you can say rotational kinetic energy. Next, what else energies we can have? This is for rotational kinetic energy. Okay, so next, this is T, my friends. Please, take this carefully. Rotational kinetic energy. Now, if you see, these bonds are not very firm; they are flexible. So, if you see, if these two molecules are connected by a bond, we can replace the system identically as the system that's connecting two masses with a spring. Yes or no? Because these bond lengths are not constant in generally. Depending upon temperature, these bond lengths can increase because these molecules try to move, correct? So there is some elastic forces in the bonds, which means when you are heating this substance, means if this substance is at particular temperature and if these molecules are moving, then what happens, there is some vibrations that are happening here, correct? Because if you see, if this molecule tries to move this end and this molecule which is on the left tries to move this end, then definitely there exists some vibration within the bond, and you have something called vibrational energy because of the stretching of the bonds. So vibrational energy. Similarly, if you see, in every molecule there is a nucleus at the center of the molecule and at the center of the atom, and definitely there are electrons surrounding this nucleus. So these electrons are also moving, so we also have electronic movement. So we have electronic energy, or you can say electronic rotational energy. Similarly, because of these bonds and all, you have a lot of different forms of energy, like chemical energy, nuclear energy, all these things, depending upon the substances that you are putting inside. So if you combine all these things, this summation of this microscopic energies, means basically which you are calling it as microscopic energy, is contained by the system. Correct? Means that energy is lying internal to this system, means it is lying within the system. So that's why this microscopic forms of energy, summation of this microscopic forms of energy is called internal energy of the system, because all these energies are located within the system, so they are called internal energies. Okay, so we write the sum of all the microscopic forms of energies. Microscopic forms of energy is called internal energy. And this word internal energy is used for the first time in 1849 by William Rankine. Okay, and he denoted this internal energy by, it is denoted by U in general. Okay, in thermodynamics. Okay, so this U corresponds to internal energy, which is summation of all microscopic forms of energy that we discussed here, where basically these are different forms that can be present within the system. Okay, so now you have seen what is internal energy. Now if you see one thing, I would like to write one statement. Microscopic form of energy is unorganized and is not of much use when compared to macroscopic energy. Okay, so now if this is the case, see here, because I will tell you why. Okay, so now let us suppose there is a big tank here. There is a very big tank of water, of course, for which you have small outlet like this, okay, which is directing towards this. Now if you see, let us suppose there is a wheel inside this, okay, which is connected to some shaft inside this tank. Okay, there is some hatching. Okay, let me draw some big diagram so that you can see the things in a more viable way. So let us suppose there is a tank like this, and for which you have an outlet here. Okay, so now see here carefully. Let us suppose there is a wheel inside this, okay, of course, which is coupled to a shaft somewhere here. Okay, so now let us suppose this wheel has some blades, so that if you provide some work for this, definitely they'll start rotating. Okay, so let us suppose there is one wheel, and also let us suppose there is one more. Okay, let me change this ink. So let us suppose there is one more wheel here, which is again having something like this. So this is rotating basically. I mean, it's not rotating, it's stationary. Now if you see, this is the system which is having some mass. So let me plot this mass with white color. There is some system, means basically some gas that is contained inside. Okay, so now tell me one thing. Because of the random motion of these gas molecules which are inside this tank, will the paddle wheel rotate? I mean, will the wheel which is connected here rotates? No, because the work is unorganized. Because if you see, for example, let us suppose this molecule is making an impact in this direction to rotate this wheel, then definitely there will be some other molecule which is hitting like this with some other velocity so that there is no net motion. Correct? So likewise, if you consider random motion or collisions from all directions, the work is in unorganized form. Means we can't make much use of this work to have some mechanical work. Yes or no? But if you see, if all the gas particles, let us suppose, are coming. Okay, let me change the color. So let us suppose all the molecules are coming in such a way such that every molecule has some velocity v. So you are streamlining the things now. Now, is this energy which is actually unorganized here, but when it's getting organized by the time it is coming here, is it capable of rotating this wheel now? Yes, correct. Because it's like you have an impeller and a jet is strike move on that. Correct. So if you see here, we say there is some defined velocity for this system as a whole. Here, if you want to define velocities, you need to define for each and every molecule separately. Means you need to go for microscopic approach. But here, if you talk, you can tell velocity of the fluid in this pipeline is this much. Correct. So by giving some macroscopic value that defines the value for the whole system, you can convert this unorganized form of work to organized form of work basically. Okay, so that's why if you see this microscopic motion is generally less organized but compared to macroscopic motion. Are you all clear with this so far? Is there any issue to you? Are you all okay with this? I need responses. All of you. See, I want some 20 on live. So tell me, is that okay to all of you? Okay. Okay. So see here. So basically the energy which is in unorganized form here, because you can see there can be two different molecules at the same instant, so that the net effect on this impeller can be zero. But here, when you are channelizing the work, means when you are channelizing this microscopic form of energy to some macroscopic conversion form, then you have some useful work here. Okay, so if that is clear to you, we'll go for next things. Okay, so now mechanical forms of work. Mechanical forms of work. Okay, so see here, mechanical forms of work. First of all, I would like to say something called displacement work. Displacement work. Okay, in last class, some of you asked me to give me the formulas for different forms of work, and I told you I'll be giving it in the next lecture. So this is displacement work. So generally, if there is any block that is moving in this direction, and if there is some force F that is acting, and this force F is responsible for transplanting this block from this position to this new position. If this is position A and if this is position A dash, and if both of them are defined by a distance S, then this work done is equal to F into S in displacing the body. Correct? But it's not mandatory that all the time your force remains constant and the motion is uniform. Correct? So if F dot S is only valid only if this force F is a constant value, both numerically and in direction sense. Basically in one dimension we are dealing the cases. Okay, so if this is the case, now tell me one thing. Let us suppose we have a piston again. Okay, so let us suppose we have a piston, something like this, cylinder basically. So we have a cylinder. So let us suppose we have a piston inside that. Okay, we have a piston inside that. So let us suppose this is the piston that is sitting inside with this. Okay, so now let us suppose this is the piston that you are talking. Now at any instant, let us suppose this is the pressure that is exerted by the gas. Okay, so whenever there is gas, definitely there will be some collisions that are happening. So definitely you have some pressure of gas that is exerting some force on this piston. Correct? So now if you draw free body diagram of this piston, neglecting this friction at the ends and all. So if you write this free body diagram for this piston, This piston is this way, and if you write the forces on this, first of all, you have this pressure acting like this, and next you have some weight that is being acting because of the weight of the piston. Correct? This is pressure P into area of the piston. Means basically cross section of the piston. Correct? So area of the piston. So if you see, that's the free body diagram for the piston. So now if you see, let us suppose this pressure P is capable of putting up this piston by a distance small displacement x. Means let us suppose, because of this pressure P, let us suppose there is slight movement in the piston, which we denoted by this. Okay, so see here. So let us suppose this pressure P has pushed this piston to some extent like this, and let us suppose the distance between these two points, means this is mean position in first position and this is mean position in second position. Let us suppose this distance is dx. Okay, so let me write this clearly. So this distance is dx, means this pressure P acting on this piston has moved this piston by a small amount dx at that particular instant. Okay, so if you want to talk about work, pressure is in the vertical direction, and also this this piston has been displaced by amount dx. So therefore displacement work if you want small del w. I'll show you why I'm writing del here, because generally in mathematics we have a standardization for point functions, means whose value change is denoted by the points itself is denoted by ordinary differentials small d, but whose change is differentiated by path functions will be writing del. This is the standardization in mathematics that you have for path functions, means whose change depends on the path of the process will be written by this symbol del. Okay, is equal to, now see, let us try to write the expression here. Now what's the force acting on this piston from moving from this initial position to this final position? P into A of the piston. Correct? So force is P into A of the piston into the instantaneous pressure P has moved this piston by a small amount dx. So if you write this, this implies del W is equal to P into area of piston into dx. So now see carefully. If this is area of piston, and if this is, means if you see the cross section from the top, you have a circular piston into this dx, which means this can be written as P into change in volume dV. Correct? Because this area of the piston into this small displacement is nothing but dV. So that's why this piston displacement work, means basically if you see the boundary is getting displaced, so the boundary displacement work is given by P into dV. This is instantaneous, because if this is the case of a constant pressure, but it need not be the same all time. Correct? So this P need not be uniform throughout the process. So in general, the instantaneous at a given instant, this P into the small change in the volume in that particular instant. So when you take a little small interval of time, at that small interval of time, what is this pressure P that's acting, and what's the small displacement that you have is given by P into dV. So therefore you can write piston displacement work is equal to same as boundary displacement work. Means basically when you are displacing some quantity, some physical object, so boundary displacement work is equal to P into dV. Okay, but see here we can write boundary displacement work only if the system is closed. Correct? Because for closed system all the entities are closed like this. Okay, so this is one form of work, which is displacement work actually. So now is equal to del W. Okay, so if you want complete W, this implies W is equal to, you can integrate PdV within the volumes V1 to V2. Okay, so because if instantaneous small work is double PdV, and if you want total work, then you will go for integration from initial state of the piston to final state of the piston. Okay, so this is formula for displacement work or boundary displacement work of the piston. Next, if you see one other form of work after this, you can, yeah, I'll tell you, Nagaraju, work causing boundary interactions. I will deal things, but let us right now. My intention is only to show you what are different forms of work that we are involved with. What are basically different mechanical forms of work. Okay, so after this, we will go for the rest of the things. Okay, so next, shaft work. We will see all these kinds of work, how they cross the boundaries and all. Okay, so shaft work. So if you see shaft work, so let us suppose there is a mechanical shaft which is rotating at n rotations. Let us suppose because of application of torque T, this shaft rotated n rotations. Then what is work involved? Means for rotating a shaft by applying a torque T for n rotations, what is the work that is needed? Okay, so see here. If this is a radius of the shaft, for example, this torque is equal to force into radius. Okay, so this implies what is force? Torque divided by radius. Okay, so now to define what is the displacement, because mechanical works are nothing but force into displacement. So what is the force that is trying to rotate this member, and what is the distance you need to you need to identify what's the distance that every particle on this object or shaft is moving. So for example, if you take a particle on the surface of the shaft, then what happens? For every one rotation, this particle covers a distance of 2 pi r. Yes or no? Okay? So for every one rotation, this particle covers a distance of 2 pi r, which is actually the circumference of the shaft. So if you see, if it is rotating for n rotations, then what's the total distance it's covered, or total displacement it's covered? Of course, in this case, total distance actually, not displacement. So if you see total distance covered by this point for n rotations is distance covered is equal to 2 pi r is actually 2 pi r is actually the circumference of this shaft, which is the distance moved by this particle for one rotation of the shaft. So if you go for n rotations, you can have into n. Correct? Yes or no? So therefore, work done is equal to force into displacement. So if you see, force is T by R. So force into distance moved by this particle into this. So 2 pi r into n. So 2 pi r into n will give you, cancelling this r, this will give you 2 pi n into T, where T is torque. Okay, so this is formula for shaft work. Therefore, shaft work is equal to 2 pi n into T. Okay. Now, if you want to convert this into power, generally because shaft works and all, they'll be denoted in terms of power. So you need to know how many rotations the shaft is rotating for a given minute, and you will divide the time accordingly. Okay, so then this will be angular velocity. 2 pi n by T is angular velocity. So torque into omega will give you shaft power. Okay, but this is formulation for work actually I'm giving you. Okay, so n is the total number of rotations this shaft has rotated by the application of this torque T. Okay, so now work done in compressing a spring. In compressing or in stretching, doesn't matter, it all depends upon sign. For compression, you need to put the work, and for expansion, that work done is generally stored as elastic energy in a spring. So work done in stretching a spring. In stretching a spring means basically when there is a spring, because sometimes we see systems where this piston here is connected to a spring. Okay, so if that's the case, then we need to know by the movement of this piston, the spring length gets changed. So you need to know what's the work interaction that is involving when you are stretching or closing this spring. Okay, so therefore, let us focus on this spring element as well. So work done in stretching a spring. Okay, so let us suppose there is one spring initially whose length is x1. Okay, now let us suppose you applied some force and you stretched the spring to some new length x2. Okay, with a force F in general. And this force may be constant or may not be constant depending upon the things. So now if you see, if you know something for stiffness of the spring K, which is basically denoted by stiffness, so stiffness K is equal to F by X. Okay, in general. So if you know this, K is nothing but F by X, because the force you need to provide a unit deflection in a given spring is called its stiffness. And generally, if this stiffness is very high, then your shock absorbingness will be very more in general. Okay, so this implies, so see here, F is equal to K into X. Okay, so now let us suppose for small quantity of stretching, for dx quantity of stretching, work done in stretching a spring is equal to, let us suppose small work we are considering, del W is equal to, for stretching a small distance x, so Fx into dx for small distance. So if you want for complete work, for complete stretching from position of length x1 to x2, then you need to integrate this from positions x1 to x2, F into x into dx. And let us suppose this F is a constant, generally we assume that. So if you take F, then integration of x dx, in mathematics there is a result in integration. So x power n dx is equal to x power n plus 1 divided by n plus 1. Correct? Plus constant, of course. So since this is definite integration, we don't consider that constant. And since n value is also not equal to minus 1, we can apply this format. So if you apply, you have x square by 2 within the limits x1 to x2. Okay. So therefore, W of work interaction from spring is equal to half into F into x2 square minus x1 square. Okay. So yes, so sorry, this is K, right? Because force is nothing but Kx, so we made a mistake. This is not Fx, this is Kx, because force into displacement, so Kx into dx, because this force is given as Kx, so this is not Fx, this is Kx. So if this is Kx, we should replace every term with K basically. So if you see, we have Kx into dx, so K into x square by 2, and this is K. So half K x square by 2 minus x2 square by 2 minus x1 square by 2, which is in general you term this quantity as potential energy of the spring. So if you see, because we need to know this dx, we are taking only for a small stretching. So if you want to know full stretching, then you need to calculate this value from integral x1 to x2, like how we have done in the previous case for evaluating displacement work. For this PdV, to get the complete work, we integrated the things from V1 to V2 in a similar fashion. We will evaluate this thing. So this is basically the spring work that we do in stretching a spring. Okay. Correct. So these are different forms of mechanical energy that we deal with in general in thermodynamics. Okay. So I'm going ahead now. If you go back to our discussion of energy of a system, because since I talked about kinetic energy, so I thought of writing this force into displacement and all these things. So if you go back to kinetic energy, total energy of a system. Total energy of a system. Total energy of a system. So this total energy E of a system is equal to two quantities, which is E macroscopic plus E microscopic. Correct? This is what we stated at the beginning of our lecture. So if this is sum of macroscopic energy and microscopic energy, so in general this macroscopic energy is equal to kinetic energy, which is macroscopic of course, plus potential energy in general, because these are the two macroscopic kinds of energy that generally exist in a gravitational field, because of this P exists because of this gravitational field, because of some elevation, because of some change in elevation with respect to datum, and this kinetic energy is because of the translation of the body as a whole, macroscopic energy plus E microscopic. So in case of E microscopic, you need to add all those quantities which we discussed. Like if you see translational energy of molecules, then a rotational kinetic energy of molecules, chemical energy, nuclear energy, all these energies will add. But it told all forms, summation of all forms of microscopic energy is named as internal energy. Correct? So Ke plus Pe plus U, since there is no energy associated with mass interactions here. So therefore, this is the total energy of a system. So now, if system is stationary, if system is stationary, if system is stationary, see, of course, I defined it only for closed system because when when I didn't assume any new mass coming out when writing this different forms of energy for this U. Okay, if there is some mass coming, there is some other energy called flow work which is possessed by the system, but for the time being, right now I am not dealing that. So we are dealing this only for closed system. So this E of system is only for closed system. Okay, because when writing different forms of U, I didn't mention something called flow work, which is actually we'll discuss later when we are dealing energy analysis of open systems, chapter number 4 in our discussion. Okay, so this is for closed system. Okay, so now if you see, if system is stationary, so generally if you see all your applications like boiler, turbine, they'll be sitting at a point because they don't move across the plant. So if they are sitting at a point, these kinetic energy and potential energy terms are generally zero, correct, or very small when basically zero, because you'll fix the power plant. I mean, in a power plant, if you take boiler, you'll fix that to at a point so that the boiler don't have any macroscopic motion. You can't see a boiler running in the plant, correct? So if you see that case, this energy possessed by the system is equal to internal energy. Means basically all the macroscopic motion is arrested, so you have only microscopic motion. So E of the system is basically equal to internal energy of the system, which is contained within the system. Okay, so this is for stationary and closed system, because we didn't give expression at for open systems. Okay, so stationary and closed systems, energy possessed by the system is equal to internal energy, which is U. Okay, so basically this is how you will be writing different laws that are governing the equations by taking the energy of the system is just the internal energy. Okay, so is that clear so far? Can we move ahead? If yes, please say yes, we'll move ahead. All of you, 25 people are watching, so please say. If all of you are okay, we'll go for the next step. We'll talk about heat. Yes. Okay. So now let us talk something about heat, because we talked something about work till this point. So we'll talk something about heat. Heat. Okay. So, heat is a form of energy which transfers from one place to another place by virtue of temperature difference, correct? So we can say heat is a form of energy. Heat is the form of energy. Heat is the form of energy that transfers from one point to another point, by virtue of temperature difference. So for the heat transfer, what's the main source? You should have some temperature difference, correct? So by virtue of temperature difference. So in PDV work, why don't we consider the weight of the piston? So in yesterday's class also I have told you, in general, this pressures inside the if you look at IC engines and all, this weight will be very small. And of course in equilibrium, even if you're writing PA dx, this is same as W into dx, which is weight of the piston, correct? So either by putting P into A or W, both are same because the piston has to be in equilibrium. Once it's at see thermodynamics, we are discussing only about equilibrium process. I told you on the first day there is something called thermodynamic equilibrium where the system is obeying all these conditions. So if you see either writing PA into dx or W into dx is same because if the piston is in equilibrium, see I have stated this diagram here if you remember. If this piston is in equilibrium, as per statics, sigma Fy is equal to 0. So means basically the net vertical force on the piston is 0. So P into area of piston is same as W into piston. So if I put P into A of piston or if I put W, both are same. Okay. Okay. So now, clear? So now if you see for a closed system, if there is some energy interaction, which is other than heat, it is definitely work interaction. Either it can be of any form, it can be electrical work or mechanical work, some other forms of work. But if at boundary, if there is some energy interaction, and if that energy interaction is not heat, then definitely it is work for closed system, because in closed systems we don't allow the energy to come in by virtue of mass transfer. Correct? So that's why any energy interaction at the boundary of the closed system, which is not heat interaction, is called work interaction. Okay. So in generally, if you see some books, they set up different definitions for work. Work is said to be done when the sole effect on the surroundings is to raise some heights and all these things. But purely that's all depends upon the only setup that you are putting, the kind of apparatus or the kind of design setup for the experiment that you are using. But generally, for a closed system, if there is some energy interaction that is happening, and if it's not heat, definitely it should be work. Okay, because energy can transfer either through heat or work or mass, but in closed systems we don't allow any mass interactions to the system or out of the system. So that means this is work interaction. Okay, so now if you see clearly, so both heat and work are boundary phenomena because they will be observed only when they are crossing the boundaries. Correct? So we can write both heat and work are boundary phenomena. Both heat and work are boundary phenomena because if you are saying there is 100 kilojoules of work transfer to the system, then from where this 100 kilojoules is entering to the system? Just by crossing the boundary. Correct? So likewise, if they are happening, means when they reach the boundary, only then we can identify them as energy interaction. Means for example, let us suppose this is a system, okay, and suppose some energy is getting transferred from this point to this point. Let us suppose some heat which is here is getting transferred to some point here which is at lower temperature, and if you take this complete part as a system, then we can't say there is heat interaction to the system. Correct? Because I told you inside the system energy transformations can happen, or energy interactions can happen, but we say there is some energy interaction to the system only if it is crossing the boundary. Correct? So internally anything can happen, it doesn't matter, but when it is crossing the boundary, we talk that as energy interaction, because I told you in open systems energy interactions takes place between system and surroundings, or either from one system to another system. Correct? But not within the system. Correct? So if you remember this, since both are observed because they are observed only when they are crossing the boundary. Only when they are crossing the boundary. Only when they are crossing the boundary. For example, if you take internal energy is not a boundary phenomena, because if you see internal energy is possessed by the system, and internal energy is nothing like It's not like internal energy is going out of the system or coming out into the system, but generally heat and work are the energy interactions that are going out and coming into the systems across the boundary. So if you see this, both heat and work are boundary phenomena, and they're generally observed only when they deal with crossing the boundary. Okay, so see here. Okay, so this is the point. Now, how to identify which type of energy interaction is happening? Okay, so we told heat and work interactions we observe only at the boundary. So we look which form of energy it can be either heat or work which is causing the boundary. Okay, so let us have some explanation on that now. So for that, let me assume one rigid container. Okay. Just a second, let it be responsive. Okay. So see here, let us suppose there is a rigid tank like this. Okay. So now if you see, and let us suppose there is some electrical heater within this. So let us suppose this is some electrical heater that is sitting here. Now let us suppose there is some gas inside this. Okay. So in this rigid container, let us suppose there is gas. Okay, so this is my system, which is gas. Definitely, Ajay, there is some temperature changes that happens. Okay, so see here. So this is gas and this is electrical heater, which how the electrical heater operates in generally. Suppose if you are providing some electrical work into the system, W electrical, then this electrical work means basically by giving it to some supply to this, if you are supplying some electrical work, the main source of this heater is to convert that work into heat energy, correct? So it converts this W into heat and it provides it to the gas, correct? That's what a electrical heater does. Barely it takes electrical work and converts it into heat energy and it supplies to the system. So if this is the case, so see here. Now if I take my gas as the system, okay. Now let us say case A. Gas is the system. System is any quantity of matter. So since this is some quantity of matter which is confined in a rigid container where mass interactions are not possible, so if you see this gas is the system, and if you try to draw the boundary for this, this is how the boundary looks like. For the gas, if I take gas as a system, then this is how the boundary looks like. So now if you see here, if this white dotted line is the boundary, what type of energy is transferring the boundary? Is it work or heat? If you see, if this is boundary, from this point some kind of energy is coming from this particular point heater. So if you see which kind of energy is causing, is it work or is it heat? Which is causing the boundary? Which form of energy? All of you. I want all of you to respond. Yes, all of you to respond. Heat. Correct? Venkat Nagisai, you are correct. Heat. All of you. I want all of you to respond. See, you can clearly see there is some heat that I have done here that is causing this boundary. Yes or no? Heat. Heat. All of you. Heat. Heat. Correct. So if you see, heat is transferring across the boundary. Yes, correct. Heat is transferred across the boundary. Across the boundary. So you say there is heat interaction, which is of course into the system. Correct. Now let me draw the same diagram and let us consider some other system. Okay. So now let me draw the same diagram for you. So let me draw the same diagram for you. Just a second. It's responding. Because I want the diagrams to be neat, because I am giving you notes. Okay, so that's why. So see, let us suppose there is again a tank like this. Same tank, a rigid tank. The same tank, I am considering it here. Okay, and let us suppose again there is one heater that is sitting here, which of course it's giving some work input and it's again giving some heat into the gas. Okay, because generally the purpose of the heat is to convert electrical work into gas. Now let us suppose this is again gas that is contained within the system. Let us suppose this is gas that is contained within the system. Okay, so now see here. Now in case B, this is case A basically, and let us suppose this is case B. Now in case B, if I consider container along with gas is system, container along with gas is system. Okay, so if container along with gas is system, then what could be my boundary? See here, I'm drawing my boundary here. So my boundary is something like this time, because I need to include my container and also my gas which is lying inside that container. Okay, so if that's the case, this will be my boundary. Yes or no? Tell all of you, is this my boundary in this new case? Correct, same setup, but my choice of system is different this time. I have considered this container along with this gas as system. Then is this yellow dotted line is my boundary? Yes or no, all of you? Yes or no? Please tell me. No? See, I considered my container along with gas as a system. Yes, okay. So now see here, actually when I took my system, the boundary is nothing but the entity that separates system from surroundings. So if I take this system, this white line as a system, I mean this white box which is here, basically my container that I'm assuming as a system, then the boundary should be definitely out of the system, which is separating this system with surroundings. If that's the case, then see what happens. Now what's the kind of energy that is transferred into this boundary? If you see at this boundary point where some energy interaction is happening, is it work or energy that is causing the boundary? This is electrical work that is coming into. Until the point it comes to this device, it is electrical work, correct? So if you see work, correct? So that's therefore we say work interaction is taking place, because the form of energy that is crossing the boundary is work. So we can say work interaction is taking place. Basically, it is electrical work in this case. Yes, this is. Yes, because since this work interaction is not happening because of this temperature change, this is definitely work interaction, correct? Because I told you energy interactions that are taking place between the system and surroundings of a closed system, which are other than heat, are called work interactions. So if you see, for this electrical work to go in, there is no temperature driving potential. Temperature difference as a driving potential for this work to happen. So if you see, this is a work interaction. Also, you can see by the definition of the interactions that I stated as boundary phenomena. If you see here, the electrical work is causing the boundary. So in case B, we define this energy interaction as work interaction. So for the same apparatus, depending upon the choice of the system, the type of energy interaction changes. Are you all clear with this so far? Is that okay? If that's okay, we'll move for the next step. Is that okay to all of you? I want all of you to respond. If there is some doubt, you can ask me. I'll let you know the things. If everything is fine, it's okay. Then we'll move ahead. So did you identify, depending upon the system, how to identify energy interactions that are taking place? If that's okay, we'll move ahead. Okay. So see here. So now we have seen basically what is work and what is heat. So we have seen different mechanical forms of work, and we have seen total energy of a system. Basically, it can be of macroscopic form of energy, or also it can be of microscopic form of energy. So if that's the case, see here. So let us take a closed system again. Oh, sorry for this. Let us take a closed system like this. Okay, of course, let us suppose this is the piston. It got hang, yeah, see here. So let us suppose this is a piston that is sitting here. Okay, so fine, see here. Now let us suppose there is gas inside this. Okay, so let us suppose there is some gas, which is my system in this case. Now let us suppose there is some energy inlet to the system. Okay, of course this is piston. So let us suppose there is some energy inlet into the system. Okay, so that energy inlet, I am writing it white with white. Let us suppose there is some energy inlet to the system. If I take this gas as a system, then let us suppose this gas as a system. Okay, then let us suppose some energy is going into the system, and also some energy is coming out of the system. I'm talking about energy, I'm not talking about heat or work. Okay, it can be of any form, it can be either of heat form or it can be of work form, doesn't matter. I'm talking only about energy interactions. Now if you see one very important thing, you have law of conservation of energy. Correct? Means basically if something is some energy is going into the system, and if something is coming out of the system, and if you see E of system, means basically energy of system is denoted by E system at any instant, then you have energy inlet minus energy outlet is equal to change in energy of the system. Generally you denote changes by deltas in mathematics. So delta E of system. Correct? This is what you have as law of conservation of energy. Law of conservation of energy. Law of conservation of energy. Correct. So now if you see, I told you both heat and work are path functions because they depend on path. I'll tell you why. Okay, we know work is a path function. In few cases, after a few moments, or maybe in the next lecture, if time permits, we'll we'll work out different expressions, and I'll show you why work is a path function. Okay, if gas is system, then heat energy. If gas is the system, then there can be heat energy or there can be work interaction also takes place. Padu, I'll show you. See here. Let us suppose this is some system, closed system. This is gas. Okay. So now if you see, let us have a paddle wheel like this. So if by some source, if I rotate this paddle wheel, then this paddle wheel which is here will actually provide some work input to the system, because this energy transfer is not because of temperature difference. Correct? So likewise, Padu, you can have even work interaction for the closed systems. Okay, when you are putting a paddle wheel kind of thing, and if you are rotating, the energy interaction that is happening is not because of temperature difference. Okay, so if this is the case, so I told you heat and work are path functions. So I told you in mathematics, path functions are denoted by del symbol, and exact differentials of point functions are denoted by small d symbol. So if you see, for closed system, for closed system, executing a process means, let us suppose because of some energy, let us suppose we are adding some heat. So what happens then? This, pressure increases inside the system and this piston starts moving. So let us suppose some process is happening because of some energy input. Okay, because of some energy input, some process is happening. So then this implies E in minus E out is equal to, see, let us assume the system is stationary, because piston cylinders are generally devices like boilers and all, they all sit at a moment. So assuming stationary system, now if system is stationary, what is energy of system? It's nothing but internal energy. Correct? We have shown you in the beginning of the class today. If system is stationary and if it's closed, then definitely total energy of the system is equal to internal energy of the system, the energy that the system is containing, correct? So this delta into this E of system is nothing but U. Yes or no? Because I told you the energy of a system which is closed and which is stationary is only internal energy. So if you see the things, this E of the system, change in energy of the system, is nothing but change in this internal energy. Now if you look back to thermodynamics, the main motto while defining or while developing the subject of thermodynamics is to provide some heat and to get out some work, correct? So by providing some heat to a system, you should get some work output. That's the main motto at the introduction of thermodynamics, correct? So this energy input, let us suppose we are giving heat, so small amount of heat, because we are writing small changes. So if you see, so let us write Q here. Let us suppose we are giving Q. This Q is the amount of heat that we are giving as input to the system, and we are expecting a work output W from this. Generally heat is denoted by Q, so I am writing Q, and this energy out, which is basically the work output that you are expecting from the system. So this work output they have denoted by W, and this is equal to delta U for a this equation is valid only for a closed stationary system, because you neglected kinetic energy, macroscopic kinetic energy and macroscopic potential energies you have neglected. So for a stationary closed system, if you see, this is Q minus W is equal to delta U, because the main motto is providing some heat input and getting some work output. Okay, this is for a process. Okay, so I told you for a process here, executing a process. Okay, so for a process, Q minus W is equal to du. So if you write this equation one more time, this Q minus W is equal to delta U is called, this equation is called first law of thermodynamics. First law of thermodynamics for a process, because this first law is nothing but law of conservation of energy, and you have seen this we have deduced only from the conservation of energy principle. Okay, so energy inlet minus energy outlet is equal to delta E of the system. So if you see, this is called, this first law of thermodynamics is also called law of conservation of energy. Law of conservation of energy, because we deduced this purely from energy conservation laws. Okay, so now if you see, this is a total energy change within a process, but generally in process, while executing a process, all the parameters need not be constant. So therefore this is also written in differential form, means for small terms. This is for the complete process. So if you want to write for the small terms, you can always write del Q minus del W is equal to du, where these are differential terms. Both equations represent the same thing. This is just differential form including small changes. This is for the complete change of the process. Okay, are you all clear with this? Did you all did you all understand how things are happening here? Is that understandable to all of you? If yes, please say yes. We'll move ahead. Or else if you have some doubt at any point, you can ask me. Very clear, Padu? All of you, please respond. Nearly some 20 on live. Crystal clear? So happy? So see here. So if this is the process, now the conventions for signs, basically sign convention. When you are executing some process, you should have some sign convention. Like for example, in bending moments and all, we define a counterclockwise sensors, positive and all these things. So similarly here, the main motto of thermodynamics is by taking some heat, the device should provide some work output. Correct? But instead of providing some work output, if it is consuming some work, which are later applications that were developed, like refrigerators and heat pumps and all these things, which actually consume some work. So if you see, if generally thermodynamic devices are at the introduction of the subject, thermodynamic devices are designed to develop some work output. But if they are consuming some work output, then those machines or those devices are considered as negative devices, because instead of supplying work, they are consuming work. So they are called negative devices. And sign convention is given as work done by the system. Work done by the system is taken as positive effect, because as expected, when you are giving some heat input to the machine is capable of giving some work output. So this is treated as positive. First law of a cycle, Ajay, let me please explain you. Let me give, please give me some time. I'll go for a cycle as well. Okay, no issues. So work done by the system is positive. Work done on the system. So if you are providing some work into the system, so work done on the system, work done on the system is negative, or work supplied to the system in general. Okay, so if you see, this minus sign we have only when we are expecting. See, we got this equation by assuming the output is work, correct? But by somehow, if your work is getting inside, then you need to replace the value of work with a minus sign here. That's why I told you this convention. Okay, because we got this minus sign only by assuming work is coming out of the system, correct? So if we suppose if we have assumed work is going into the system, then we might have put a plus sign here actually. But we assumed that work is coming out of the system, so we put a minus sign here. So this is the sign convention that we have here. Work done by the system means system is providing some work. Means, for example, let us suppose in this piston cylinder device, by producing some heat, this gas pressure is increased. So this is pushing the piston. But in a worst case, if this piston is pushing the system, then we say work is done by this piston on this system. Okay. So in general, if you see, generally by providing some heat input, this work output is generally from here with the in the view of direction, in the view of displacement of this piston, which is actually the mechanical work this system, this gas is doing actually when I am supplying some heat. So such kind of works where system is doing some mechanical work is called work done by the system. But in a worst case, if you are pushing this piston, or if you are generally you do that in compressors and all, because for compression, you need to supply some work input and you will try to do some work on the gas. So for such kind of devices, work done is on the system and it is treated as negative since the device is consuming some work. Okay. So similarly, if you go for heat convention, heat added to the system, heat added to the system, heat added to the system is positive. And similarly, what is heat rejected by the system? All of you? Heat rejected by the system, what it is? Heat rejected by the system is negative. Because as I told you again, the device should always will to take some heat and provide some work. But if the device is not willing to take heat, means if it is rejecting heat, then it's called negative nature of the device basically at the time of introduction of this subject in long back in 80s. So this is treated as negative. Yes, negative. Because condensers and all, they generally take out heat from the systems. So this is the sign convention that we follow while adopting this equation, because here we got a plus sign because we considered that heat is added to the system. So that's why if you see, heat added to the system is positive. Here, E inlet. Similarly, work done by the system is positive. Similarly, because we assumed this work is coming out of the system. So that's why minus E out, we have put a positive sign for W here. So is that clear with sign conventions to all of you? If that's clear, then we'll move ahead for a bit. Is that okay to all of you? Can I move ahead now? Now, I hope you all understood why these sign conventions are taken in this way. Okay, so see here, we'll be going for the next step. So now we have seen, displacement work by the piston is integral PdV. Correct? Now, depending upon the process, this P may be constant if there is a constant pressure process that's happening, and similarly, this P can also be variable depending upon the process that's happening. Okay, so we'll see work interactions of different kinds of systems basically when they are closed. Okay, so for closed systems, we'll define what are the properties. What are the work done that are happening. Similarly, for heat interactions, we'll define formulas and all these things. Okay, so before going for that, I would like to tell one thing for you: specific heats of substances. Now, tell me one thing. You might have learned this definition of specific heat in your schooling, correct? What is the definition of specific heat? The amount of energy required to raise the temperature of a substance by unit mass, correct? The amount of heat required to raise the substance temperature by 1 unit when the substance mass is 1 unit. Correct? So if you see, means basically if you are taking one unit mass, basically in SI units, if you take okay, 1 unit, let me write 1 unit. So if you heat this, then definitely what happens? By some source, let us suppose you are heating this, then the temperature of this block will start increasing. So when this is of unit mass, then this energy required to raise this T by 1 degree centigrade. Correct? So see here. Now this heating, okay, you can write the amount of energy. The amount of energy required to raise the temperature of unit mass of a substance by 1 unit. Correct? Now, when you're heating a body, you can do it at 2 different conditions. One is at constant volume, like generally you'll be heating solids and all these things, and generally another is at constant pressure. So first of all, if you define specific heat, you need to define at which condition this is getting happening, because if you see, the amount of energy changes when you are heating at constant volume, and if it is some other value if you are heating at constant pressure. So let us look at two important definitions at this moment: specific heat at constant volume and specific heat at constant pressure. So let us write that. Specific heat at constant volume. Specific heat at constant volume. Okay, so this complete definition comes here, but in the last it will add at constant volume. Okay, so let us write that 5y. Let us spare some time in writing that. The amount of energy required to raise or not. If container along with gas is a system, then will heat interaction takes place or not? There can be heat transfer, because if you see, if container is not insulated, then definitely some heat can flow in if there is temperature difference. Correct, Padu? Did you understand? See, if there is no insulation, and let us suppose you are having some ice cubes as your system, which is having some mass, then what happens? Heat gets flown inside. Okay, so see here, required to raise the temperature of unit mass of a substance by 1 unit at constant volume. Okay, at constant volume. So now see very carefully. I would like to give you one formula here. So that formula is very important for us in analyzing the systems. Okay, so see here. So which means, if you let me denote this as CV. Okay, so CV, so means CV is equal to del Q, means the amount of energy that is applied, divided by del T, since temperature is a point function, you can write dt, and let us suppose we have taken unit mass of a system. Okay, so this is unit mass at constant volume. V is equal to constant. Let us suppose we are writing into m dt, because for unit mass and unit temperature change. So this is definition of CV. But now if you observe something, we mentioned one important word here: volume is constant. So let us consider one system which is having some physical significance here now. So let us suppose we have some system like this, and let us suppose this system is a rigid container. This system is a rigid container. So if this system is a rigid container, rigid in the sense, you know what is a rigid body? Generally, whatever you do, the dimension or the volume of the body doesn't change, correct? So let us suppose you are supplying some heat to this. Let us suppose there is gas, and let us suppose you are doing some heat addition process. Some Q, small amount of heat you are adding, and you know this rigid container is a closed system, of course, and it's stationary, it is sitting somewhere. Then you know this system is not capable of doing any boundary work because container walls are rigid, so boundary won't get displaced anyhow, as it happens in this piston case and all in earlier examples. So if you see, if you apply first law of thermodynamics for this, which I have stated as del Q minus del W is equal to du, can I write del Q minus del W is equal to du here for this process? Can I apply this first law of thermodynamics? Because first law of thermodynamics is just an energy conversion principle and it's valid for all the processes. So can we apply for this? For a closed system? For a closed system, can I apply this or not? All of you. I want all of you to respond. Whoever are on live. See, really some 20 people are on live, so respond. All of you. Can I apply this ideally? I mean, this first law of thermodynamics to this. So if I apply, now see what happens. This delta W is 0. Yes or no? This delta W is 0 because this device is not doing, this gas which is system here is not doing any boundary work. So if this is 0, can I replace this del Q with del U? This implies del Q is equal to du for constant volume process because you don't have any boundary displacement work. Constant volume process. See, generally this work interaction need not be only displacement work. It can be any of the mechanical forms of work that we discussed. Okay, shaft work, electrical work, whatever it may be. But generally this system, this example in this case is only having heat interaction but no other work interactions. So I am putting this W to be 0. Okay, so no issues. Del Q is equal to du. So now if you go back to the definition of this CV, CV is equal to del Q divided by m into dt. So CV is equal to del Q divided by m into dt at constant volume. Of course, you know when you are writing CV, that automatically tells that this is this quantity at V is equal to constant. So this means if you are replacing this del Q with this du, CV is equal to du divided by m dt. So what about du? Du is equal to mCV dt. Okay, means change in internal energy is depending upon m into CV into t. Okay, so this is how we obtain a formula for change in internal energy of a closed system basically, which is stationary. So this du is always written as mCV dt. Suppose if you want to write in specific terms, you know what are specific terms? Specific properties are the extensive properties per unit mass. Since this internal energy is an extensive property, by this time you might know why this internal energy is an extensive property, correct? Because if number of molecules increases, total energy possessed by all the molecules will also increase, which means this du is also this U is also an extensive property. So we can write specific internal energy by dividing this complete equation with mass. So this implies du is equal to CV dt, where this units of CV is kilojoule per kg Kelvin. Okay, previously the units of this is kilojoule per kg Kelvin anyhow. So see here, this is CV dt in specific terms. You can write specific internal energy. Specific internal energy. Okay, so now see here one more thing I would like to tell you. CV units. Okay, so units of CV. Units of CV. So if you see, you got du is equal to m into CV into dt. Okay, so let us talk about specific volumes here. So let me not put this V small till this step. Let me write only capital V's here. CV is equal to, yeah, here also let me, since I'm dividing it in mass, it's okay. So see here, So du is equal to mcv dt. So if you see, units of du is, u is nothing but energy, so the units of energy is kilojoules. Units of mass is kg. Units of cv we don't know yet. Units of dt is kelvin. So which means dimensions of cv is equal to kilojoule per kg kelvin. Okay, so is that clear to all of you? So now you want me to tell you this equation, how this is coming. See, if you read this definition, amount of energy to raise the temperature of the substance by 1 unit. See, suppose if for 50 degrees change you are providing 100 joules, for 1 degree change how much you are providing? 2 joules, correct? So dq by dt will generally give you the temperature, I mean the energy that you need to raise the temperature by 1 unit. But of course, all this story should happen at 1 unit mass. So you need to divide this with mass. So Cv is equal to del Q divided by m into dt. Clear to all of you? So now these are the units of Cv. So we'll go for one more specific heat, which is Cp. Okay. Specific heat at constant pressure. Specific heat at constant pressure. So see here. Again, let us write the definition. The amount of heat required to raise the temperature of unit mass of a substance at constant pressure. So generally this is denoted by Cp, specific heat at constant pressure. So this is given by Cp. Okay. So basically if you see, Cp is equal to del Q by m into delta T, I mean dt at P is equal to constant. Okay. So now let us take one such system. Okay, so let us take, this is the system, and so let us suppose you have some piston like this here. So let us extend the container to some extent like this. Okay, so now if you see, this is piston that is with us. Now there is some gas inside this at endway point. Okay, so this is gas. So see here, let us suppose we are putting in some heat input. Then what happens? Obviously, because of this heat input, now this piston is not fixed, it has some freedom to move. Then when you supply some heat, what happens? At constant pressure, because you know this is constant pressure. Why? I told you, if you draw the equilibrium of the piston, then you know this weight of the piston and this pressure acting will be balanced. Means basically pressure into area of the piston, both these terms are balanced. Now if you are providing some excess energy, this pressure increases all of a sudden inside this container, but for this weight of the piston remains constant. So for attaining equilibrium, what it happens? This piston slightly moves up, so volume increases, and you know when volume increases, pressure decreases a bit, and again this equation is getting satisfied. To raise the temperature of unit mass of substance at constant pressure by 1 unit. Thank you, Ajay. So see here, PATM you can always consider. Even if you consider PATM, this PATM is also a constant. So if you consider this PATM that is acting here, then P of gas into area of piston is equal to PATM of gas, PATM of atmosphere into area plus W. And if you see, all these three are constants, which means still pressure is at a constant value. Okay, so I'm writing all these things. So by the time you supply some heat, the internal kinetic energy of the molecules increases. So as a result, pressure increases. Correct. So if pressure increases, to settle down this, what happens because the piston has to be in equilibrium at the end of the day. Correct. So for the piston to be in equilibrium, the piston slightly displaces up. So because of some small increase in volume, again this pressure retains this value. Okay. So pressure P is constant. So in that case, if you apply this, first law of thermodynamics for a closed system, since this is closed stationary system, so now see what happens. You are getting some work because this gas is pushing this piston, so which means this pressure P which is acting here is slightly pushing this piston, providing some mechanical work by taking in some energy. So here gas is the system which is taking some heat energy into the consideration, and it's also providing some mechanical work. So if this is the case, now if you apply ideal gas equation, if you apply first law of thermodynamics for a process where this is del Q and this is del W, so del Q is equal to del W plus du. Correct? So which means this del Q, we can write this as P dV plus du. So let us substitute this P dV plus du here, and let's see what happens. Okay. So Cp is equal to del Q by m dt, which is in the first thing. So this implies this Cp is also written as this del Q is equal to del P, which is P dV plus du divided by m dt. Correct? This is what we have, which means in internal energy case, see, transitive energy, I'll tell you, heat is a transient phenomenon. I'll tell you now, sir, what is that? So please see here, Cp is equal to P dV by m dt plus du by m dt. Correct? This is what we have. Now by definition, what is this value? Du divided by m dt. This is Cv. Correct? So which means if you take all these are positive quantities, because since temperature or volume are directly proportional at constant pressure, if dt is positive, means if you are raising the temperature of a body by 1 unit, definitely this volume also increases, which means all these terms are positive that are involved here. Correct? Mass can't be negative, pressure can't be negative, absolute value. So if dt is positive, because for definition of Cp you are raising the temperature, so which means this volume is also increasing, which you are seeing here. When there is some heat input, definitely this volume is doing some work at constant pressure. So if you see, and this is definition of Cp, so if you see here, Cp is equal to P dV by m dt plus Cv. Means you found one thing which later in constant pressure case, if I would like to explain it in tomorrow's class actually, because I want you to introduce something called enthalpy in tomorrow class. So there I'll give you the complete expression for this, but for the time being I want you to observe one result here. This implies we have P dV by dt is positive, m dt is positive at constant pressure. That's all. So if this is at constant pressure, now what is ideal gas equation? I want you to tell one thing for ideal gas. By the moment I write ideal gas, you can always apply this equation, PV is equal to mRT. Yes or no? Can you apply this? So for a given gas, once gas is fixed, this means basically you will define specific heats for substances. So once if substance is fixed, this R is fixed. So since this is a closed system, this M is also fixed, and we are assuming this process to happen at constant pressure because we are talking about Cp. Correct? So if you differentiate this equation, P into dV is equal to mr is a constant into dt. So this implies P dV by m dt. This value, if you see, this value is equal to characteristic gas constant. Yes or no? So if you replace this here, this implies Cp is equal to R plus Cv, which means Cp minus Cv is equal to R for ideal gas. Correct? So I'll give you something called enthalpy, and I'll define you the terms which we are involving here at this moment. But I want you to observe one thing: the Cp is greater than Cv, because this R is generally given by characteristic gas constant value is Ru divided by molecular weight. And if you see, both of these are positive quantities. So this ratio is positive because both these are positive. So if this value is positive, which means Cp is greater than Cv. And it's obvious because when heating at constant volume, no energy gets transferred in form of work. Whatever the energy you are supplying, that energy is just increasing the temperature of the system. But now at constant pressure, what's happening? Some part of your energy that you are supplying is going out in form of work. Means all the heat that you are supplying to the system is not using not used by the system to raise the temperature of the system. So which means when you are heating at constant pressure, you need some more heat, which means if Cp is more, then del Q is more. Okay, so it's 11:32. I'll stop here. From tomorrow, this session will continue from 10 o'clock to 11:45. Okay, so since I didn't announce yesterday, I'm ending up this session now. But from tomorrow onwards, you'll be having class till 11:45 from 10 o'clock. Is that okay to all of you? Clear to all of you? Yes or no? Padu, you wrote very big thing. My thermodynamics knowledge is nil before your class. Okay, then thank you. I hope everything is going fine. So if there is some issue, you can always talk to me in the chat, or else you can message me, since I gave you my contact in the beginning. And also, I'm dealing one more course of engineering mathematics. They in the 9th lecture of basic calculus. I have provided my contact. So if you want, you can message me the questions or doubts that you have in your mind. Okay, so is that fine? We are leaving for today. So from tomorrow, please get ready for the a bit long class for 15 more minutes. Okay, so 10 o'clock to 11:45. Okay, yeah, thank you all then.